I believe we are live. Let's see if Twitch abides. Twitch does. Do we update? We do. All right, cool. So we're on week 2 here, CSE598 at ASU. We started off with this like insane assignment, I think, on exploitation primitives, where the idea was to kind of throw everything that hopefully you know already all together in one module to verify that you know the things. As I said, it is an extremely difficult course. Hopefully you realize now that I wasn't lying. The goal of this module is, in fact, to try and verify that you have some, if not all, of these skills and/or knowledge. It doesn't actually test all of these things, but it tests a decent amount. And that is our schedule. So we've got what? We got a little while, right? 28th. What's today? Oh, we got 6 days?
Yes.
Easy, guys. Hopefully, right? Because I took a look. Maybe it's changed. Maybe it's changed. Right. Well, one of the things that I didn't do in 466, but I should do going forward is take a look and congratulate our leaders, right? Our winners, the people that are just crushing the content. What do we got? So there's what, 20 challenges? Just because they don't have, for the record, just because they don't have the ASU icon doesn't mean that they aren't an ASU student or even a university student. Like it isn't a one-to-one of whether you're registered or not. But so I don't know if this acts as a student, but good for them. They're almost there, right? And this is just since the module launch. Zolagul is in this class because I know who that is. And they're moving pretty quick. That's not bad, right? A week in, 14 deep. And if we look a little deeper, that's a university student. I don't know if they're in the class, but I don't pay attention to the handle. And everyone else is kind of down here, right? And hopefully you have at least 2 points because I like 99% solved the first one.
Yeah.
Last week. So there was some progress, right? There's some people at 4. Now I ended the stream last week with I think this works. I'm not sure why. I don't want to waste more time on stream, and I think I ended the stream. I wasn't paying attention to the clock. I should pay attention to the clock this time. We'll see if I do. Because I thought I had an extra hour at the end, and I didn't. So I actually ran for the full 3 hours. I don't intend on doing that today. But what we will do, I did fix it just right after I ended the stream, although the class says it was like an hour afterwards. I don't think it was that much debugging, but we'll see. Time moves differently, right? When you're... What's that?
A couple more allocations.
No, it was 4 lines. It was 4 lines that were wrong. So like my working theory there was correct. But I want to show that the code that we were writing last week does in fact work, which is unlike me. And then we're going to take a look at some of the problems that exist in the garbage code and see what we can do to clean it up. And hopefully you guys know, or at least have some idea of how you're failing. So we can take a look at why that's happening and what we can do to fix it.
I do have a request. Is, if possible, could you dive a bit deeper in how we could use GDB just to see the T-cache, like between malloc? I think I'd be interested in seeing, like, mallocing a couple things and seeing what addresses go in and out and what gets freed, what gets malloc through GDB.
Yes,
I think
I can do that. So
very useful.
that was something I tried to do and then rapidly bailed on last week because I was like, pwn.debug should work, and then I was like, pwn.debug doesn't. Well, pwn.debug does still work. I just forgot how to use pwn.debug because it's not my regular tool. So that is definitely something we can look at, and it's something I intend on discussing based on some of the conversations that I've had with people as far as like what they're stuck on and why. So we are here. The thing that changed was before off stream, it was these 4 lines right here. And we will use GDB to see why this is bad and why changing this back is good. We'll start there. So this is where we were. If we, I think I have pwn debug, so we'll sudo GDB our challenge. Start that up. Let's have our script over here. I'm just going to add a couple blocks where we will wait. We'll have waiting after malloc. I'll have waiting after the freeze, and we'll have waiting after, I'll call it remalloc.
Just the one.
I'm sorry? Yeah, just the one. So we have that going on. Okay. So this is running under GDB. It's great. We run our exploit script. We get waiting after malloc. So at this point, where am I? I have called on connection 1, because I have R1 and R2. I've called malloc. What do we think is the state of the T cache based on what I've done here?
So linked list.
So the T cache is a linked list. That was a comment from the class here, and that's true. But what does the T cache hold? It holds freed allocations, right? So when I call malloc, have I freed anything? No. So I haven't put anything in the T cache. Now, where I made my mistake last week in my rush to use pwn debug is I didn't think about, hey, this is a multi-threaded program, right? Which I said, but I didn't actually think to myself. And what is the T in T cache? Thread. So this means every thread has its own T cache. Now, I typed info thread, and this is not pwn debug specific. Just in GDB in general, you can type info thread, you'll get a list of your threads. And you see that there's 3 threads in here. Does that correspond with kind of what I've done in my exploit? Does that make sense to me over here? I have the initial thread that I started up on the left-hand terminal. I've made 2 connections, which is why I have remote 1, remote 2. Each of those spawn off their own thread. So there should be 3 threads. There are, in fact, 3 threads. Now, what I did last week was I immediately said, oh, what is it? What's the magic command? Bins? And it says, oh, there's nothing here. But what T cache am I looking at?
I think the main thread.
The main thread. I'm looking at the T cache for the main thread. In order to fix that, I need to select the thread that I'm interested in. So thread 2, and then if I were to look at info threads, we see now I've selected the second thread. And so now if I were to type bins, I still get an empty T cache, but I'm looking at the empty T cache for a different thread, right? Right. So far, we haven't done anything where we think we should impact the T cache. So that makes sense. We hit enter on our script. Now we are now waiting after freeze. So I've now freed 4 things. Now it's important to note for our conversation here that I have malloc from R1 and I have freed into R1.
Would that have ran even though we have GDB on? Wait, we need to continue.
And you are correct. I need to continue. But I would have missed it, but it hasn't blown my leg off yet. But I have malloc from the GDB's context, the second thread, and I freed into the T cache of the second thread. So let's continue. Control C. info threads, I should still be on. Oh, I'm a liar. I expected to be on the second thread. It's a good thing we checked. So we can go back to thread 2. I should be able to say bins. And now I see 4 entries. Right? In these 4 entries, we see they're all from the same, just looking at the memory addresses, they're all from the same region of memory. You agree? An important thing to note here is that it is this region of memory. It means nothing right now. I can tell you that it is this thread's heap. And so that kind of matches what we were thinking right there when we have waiting for freeze. So let's continue again. We're going to get waiting for remalloc. I can hear myself coming out of somewhere. I don't know where it is. Radio waves, man, they're in my head. I need the tinfoil. So what do we expect to be happening right now? I've malloc from thread 1. I freed from thread 1. Where am I mallocing here?
Thread 1.
Thread 1. So should that come from this T cache?
Yes.
Yes. And so if we, again, info threads, I'm always going to info threads. Bins, we see now there's 3 entries, right? This all makes sense because everything is happening within 1 T cache, 1 heap, in 1 thread. So this matches with kind of what we've seen in 466, where there was just 1 thread, right? We didn't have to deal with parallelism. Now, did I throw? Oh, I didn't. That's sad. I should have thrown one right here. So when we're just going to have to fix this up. So I go to the end here, waiting after freeze. Cool. Cool, cool. All right, so I'm now after malloc, free. But where did I free? In the second thread. So when I'm looking at the T cache, which thread do I want?
We want
3?
Yeah.
And then if we bins and we brute force this, we see that there's 4 things in there, right? Now, there's a little bit of an oddity here that I'm sidestepping, but we'll definitely touch on it in a minute. So the question is, why did this break my exploit that I ended with last week? So
would the first thread still have 3 allocations of the cache?
So the question was, what's going on in the first thread? Well, the first thread now has nothing, right? Because what happened? I malloced them from thread 1 back into use and then freed these chunks into thread 2's T cache, right? So then when we look at what my exploit was expecting here, in my race, where am I doing my mallocs? Let's find, where am I actually doing the race? It's my demangle, PID, fork. Okay, right here. So what T cache am I trying to like exploit and play around with? Where am I doing my malloc free?
First thread.
In the first thread. Well, what did I just do to the first thread? I put things into T cache, cleared them out, and then threw them in thread 2. And then I'm over here malloc and freeing in thread 1, but we just saw thread 1's T cache was empty, which means at no point was I really interacting with or have the possibility of overwriting a next pointer because there was nothing in the T cache to overwrite. So I wasn't even really racing anything. Does that vibe? That checks with everyone's understanding? All right. So that is what I realized as I slowly scrolled up, because I assumed the bug had to be earlier or like later in the code. Like I'm doing something else right now. It was way back up here. So if instead I do this. So now I'm malloc-ing 4 things from, and this is how you should think of it. Like, word it when you say to yourself. I'm malloc-ing 4 things from the heap of thread 1. I am freeing them into the T cache of thread 1. I'm malloc-ing 4 things across here, 4 things from thread 2, and I'm placing those chunks into the T cache of thread 2. Right? This actually isn't what I would suggest doing long term. It just happens to be what I did. Now, why would I not suggest that? We'll start this fresh. Actually, let's just prove that it works. That seems reasonable, right? Now watch it not work. I haven't touched it since it fell out.
You have a time slip. Oh no.
I don't know what I have, man. I just know that this dumped it out, and I haven't touched it since. Let's see. One message one. Print. Oh yeah, because I'm waiting for hello from here. If you recall, we ran into this issue up here, and so we added a bajillion. Where is it? Where we did the second race. Fork. Here, we made this really long with this sleep. I probably don't want that. That sleep's probably a bad sleep. 1,000 seconds. It sounds like forever. Now, even if this is a fully working solution, which it should be, it can fail, and it can fail just because of bad bytes in the address. It is still running. Okay, we lost the connection. There, it did work. Good. Turns out if you don't sleep for 1,000 seconds 1,000 times, your script will terminate. And so this was the secret for my challenge here. And if you recall, the challenge asks for the secret, right? And so this did in fact leak what we're in. Now, I made the comment that I would not do in my heap warm-up this right here. This is what I was trying to reason about real quick when I was putting this together last week, but I didn't really articulate it or demonstrate it because of pwn debug. Let's go ahead and do 2. Not anymore. Start fresh so I don't break that script. From pwn import star, we're still going to have R1. And R2. I'm going to malloc 1. I'm going to malloc 2. I'm going to... Well, let's do it this. Malloc 1, malloc 2, we'll malloc 3 down here. And then I'm going to, in R2, we're going to free 2. In R1, I'm going to free 1. And then in R2, I'm going to free 3. Okay. That's enough of a mess. So check this out.
Is this for demo purposes?
This is purely for demo purposes. It has nothing to, I mean, it has something to do with the exploit, like a fail state that you can run into or something you may not be aware. Now, it's important that we articulate it with that same verbosity, Yeah. I don't know. We use our big words when we say what we're trying to do here, right? So thread one, I'm going to malloc two things. I'm going to put one of these things into the T cache of thread one. In thread two, I'm going to malloc something, and then I'm going to free the thing that was malloc from thread one into the T cache of thread two, and then I'm going to free the thing that was from the heap of thread two into the T cache of thread two.
Can I ask a question? I might be looking ahead.
No, this is why I'm gonna throw it in pwn debug, because this is like what?
Are the addresses that get malloc from thread one and thread two going to be, like, for example, if I malloc one from thread one and at the same time malloc one from thread two, are those two addresses that get malloc the same address between thread one and thread two? Or is thread one and thread two mallocing different addresses, even though it's the same index?
I'm going to look at this in pwn debug, and you can ask your question or let me know if it's been answered.
Also, I think the 2 and 3 are variables, right? So, I mean, indexes in an array. So they should be specific to the thread, right? Or
so
am I wrong?
All right.
Like 2 is allocated by thread.
So this is where let's look at an IDA, right? Because it's how would we figure out what we're thinking about here with threads and heaps and indexes and what's going on? And I know the answer, but I also am familiar with this challenge, so that's kind of cheating. If I didn't, if I hadn't seen this years ago, what would I need to do? I would need to open up this thing in a disassembler or GDB and reason about it just like this. Somebody has a question about message. Oh, you are at the end of this course. All right. These poor people in this class are not ready to learn about kernel exploitation in message. All right. I don't think they've hit the drop deadline yet. We can't talk about that. I appreciate it. Right. And I'm more than happy to talk about it. But not yet. All right. I got to lock him into this class first. Okay. So we wanted to look at the what happens when I type malloc1 and then I free, like where is this going in memory and reason about it, right? That was our question. And if we look at what was going on last week, this thing spins off a thread that calls run thread, which is a wrapper around challenge. And then inside of challenge, we want to know what happens when we type malloc. Okay, so this goes to stored, right? What is stored? Like, where is this in memory?
Yes, BSS.
It's in the BSS. Is the BSS thread local? We won't really talk about thread local memory until like Windows for an arbitrary reason, but the like not intentional. But the BSS is just a region of memory within the process, right? There's if I reference this location and then from thread one, it's the same location if I'm in thread two, right? And so this is a common location between the two threads. When I malloc, I'm throwing it into some slot that is shared. That's why we can race this stuff to some degree, right? That is part of the shared resource. Is the fact that I know this may not be the right thing. I was looking at stored. Give me challenge. There's probably stored and some reference to the pointer, right? Message. Okay. Whereas messages is also in the BSS. So stored is the thing that we are erasing, right? Whether or not the state of this pointer is considered malloced or freed, which is why we can pull this off at all, right? Is because both of these threads are referencing a common resource, which is some memory that is in the BSS. Does that answer your question? Cool. So then, now to kind of dig into, I think, where the other question is going. All right, we are waiting after malloc. Oh, that's because I didn't run do dot all over. So do 2.py, which is the file above. All right, we're at first break. So what I've done is I have malloc from the heap of the first thread. I've malloc again from the heap of the first thread. I have freed into the T-cache of the first thread, right? This is still following kind of our 466 understanding. We go into thread 2, we type bins, we let pwn.debug do its thing. There's my one entry into the T-cache. And if we VM map that, my claim is that this right here is thread, for me, thread 1, like R1's heap. Let's carry on. Check this out. What have we done now? I have malloced from the heap of thread 2, and then I have freed the allocation from the heap of thread 1 into the T-cache of thread 2. So if we go thread 3, which is thread 2 here, bins, I get these 2 addresses. Now there's something a little bit different about this scenario, because these look quite different. And if we were to VM map these, this one should be the same location as the thread 1 heap. And if we were to look at this, it's going to resolve to a different region of memory. Now, it looks pretty similar because we see 21000, but if we look a little bit earlier in the address, here, right, or we look at the left side of the region, we see that these are different regions of memory. And so when we are doing this and thinking about what's in the T-cache and what's the next pointer, and we have safe linking, where the address of the chunk and the address that we're being pointed to matter. And if you'll recall from do.py, when we had this demangle function that was just like, oh yeah, it's magic and it works, it relied on this implicit assumption that the pointer and the address of the next pointer are on the same page. What happens if I start allocating things from the heap of thread 1, I start allocating things from the heap of thread 2, and I start kind of freeing them willy-nilly all over the place? Does my assumption about the region of memory or the page that these addresses are on hold true? No, it breaks. And it breaks horrifically. Now, you could...
just to...
Yeah.
For demangle to work, you need the 2 addresses that are being mangled with each other, they need to be on the same page, correct?
So the 2 things that matter for mangling or demangling is the position and the pointer, right? We see that here with this mangle function. And the assumption that this demangle function has is that position bit shifted by 12 is the same thing as pointer bit shifted by 12. 12 bits is 3 nibbles, which is going to be a page, right? And so that is our assumption. Now, if I were to try and write a more complicated demangle function, right, because this may not hold true, I would suddenly want to have position, or I would want to have, for instance, my offset guess, right? Because I'm trying to predict the distance between these 2, and then I'm going to have to start add whatever my offset guess is to this bit shift, right? So if I think that I'm just dealing with something that is, for instance, on the next page, then my offset could be 1. I can reasonably just say, okay, we can ink something. It's on the next page, right? And that happens when you're mallocing from one heap, larger, getting larger allocations and freeing them. You're going to pretty quickly get to the next page, and you're going to have to deal with this. But that's a pretty easy thing. It's deterministic in the sense that you're the one that's manipulating the heap, so you know when you have rolled over to the next page. right? And so I can say, all right, cool, I need to increment this by 1. I malloc and tree a bunch more stuff. I need to increment this by 2. And like we can kind of work our way, from here.
So going back to thinking about this in our exploit, if I grab an address that is from a different region of memory completely from what the Tcache addresses are from, how would I decide to mangle that address so that I can like get it in the Tcache to set the next pointer with it? So what I'm saying is,
well, you already did that though, right? Like we did that when we solved our first challenge, just with this right here. My position is my heap leak.
Yeah.
Right. The pointer is a stack pointer, a BSS pointer, like in this level 1. If we look at what I did with mangle, what did I do? I took my heap leak, which I know my heap leak is on the same page as where this needs to get placed, right? Because I'm at the beginning of the heap. It's a first thread heap. No one else is touching it. So I can make this assumption that what I have leaked corresponds to the location in memory where this target address is going to be written, which is what allows me to mangle this target address. Because in our level 1 here, what is our target address? It's in the BSS, right?
Right.
And so that has nothing to do with the heap.
I think I got confused with the mangling and demangling.
No, the mangling and demangling can be pain. It is pain. It's not can be pain. Somebody says you'll have better success if you ask in Discord. Okay, hopefully that's to the kernel person. For a lot of this stuff, I know you answer quite a bit. Twitch contributor, but I answer a lot of the stuff up around these challenges. So you still get me, which is unfortunate, right? Okay. So I identified this problem that when we looked at the bins, these are now coming from 2 different memory locations. And so if we were to look at the page that this is on and the page that this is referencing, that no longer holds true, right? So that's a problem. Does anyone have any idea of what we could do to address this?
What are we addressing exactly?
So I want to avoid this scenario. Like if I somehow end up with something like this, I have created a very big problem for myself.
Make sure that when you malloc from a thread, you only free to that.
So one of the things that you would think is, all right, when I malloc from a thread, I'm only going to free from that thread, okay? But what is going on with our race, right? Where we're racing, and that means that we are malloc freeing, and that would come from a Tcache, and so you could do that, right? But one of the problems that I know people have ran into, because they brought it up, is that like they close the connection and then it explodes, right? Like all I did was R1 close. Let's see if I can do that. See if it happens over here in do.py. Where's a reasonable place to do that? Let's do it over here. R1 close, R2 close. Nope.
I want to run this through.
Maybe. Let's see if that site faults. Give it a minute. The problem that we run into is we have to pay very close attention to what is the state of our Tcache, what pointers are there, what values are there, because you run the risk of either creating a scenario like I just described. Right, we blew up over in our Python code. That's because I closed before I wrote, but I didn't blow up in my GDB code, so I don't have that problem, which is unfortunate. So you want to make sure that you can reason about the pointers and addresses that are in the Tcache is what I'm trying to touch on. The way that you can do that. There's kind of two strategies for people who have solved this module. The first is, I think, what the person who had the exploding connections was trying to do. And it's totally reasonable, is what happens when I do this race and I overwrite a next pointer. I have like broken the T cache, right? Because I've put some pointer there. The next pointer is going to be for mine. If I were to make this deeper. RC.1. Hello from here. Message. We'll see if that should. But what we'll see is the Tcache gets corrupted with that literal string value, right? That next that secret that I'm leaking, of course not. That secret that I'm leaking from the Tcache's perspective is a next pointer, right? Because the Tcache doesn't know any better. And so you end up with this corrupted, broken state. But then you're like, oh, but I need to do an arbitrary read of some other region of memory, right? I read something from, I don't know, libc. Now I need to read something from the stack, or I need to read something from the BSS. How do I do this? My Tcache is broken.
Try running it without GDB. You get that before.
You want to... I think I'm just getting unlucky there.
I know I built up. It happened to me too, but I think it only happened when I just had the server running. But
yeah. And then attached to it pauses. Okay. We can give that a shot. And so it's, I have this corrupted Tcache, and I don't get to choose another bin in this challenge, right? I don't get to choose the size and interact with. Oh, it's because I still have frickin' R close in here, isn't it? Didn't I? Yes. That helps if you remember the code that you wrote. And so how do I carry on from this broken state? I can't interact with a different bin. What do I do? There's two strategies for success. The first is just make a new connection. You have unlimited threads, so make two more connections, generate a new heap leak, and do over what you just did, right? Because every thread has its own Tcache, every thread has its new heap, and so I could take the entire thing that I've written. Let's look at thread 2 bins. Did that look like this? DHTXSM. Why does that look slightly different? It's got a mangler, right?
Oh, yeah.
I don't know if pwn debug is demangling it or not, but I would venture a guess that's what's going on there, right? But we see that the Tcache, the next pointer, clearly is deriving from this. And so the Tcache chain, that singly linked list, is broken and messed up. There's two ways to deal with it. The first is repeat everything that I have up here, like, because we're trying to write something that gives me a primitive. My primitive here right now that I have is an arbitrary read. A naive approach, although it totally works, is I say everything here from making the connection all the way until I print out my thing. This is get read at target, right? And we just define this like this. I'd have to clean up some things because I don't want to lose. Like right now, this would work because if I were to call get read of target address, my connections are scoped to this function. These would automatically close when I leave scope. If things are broken in such a way that the T-cache gets interacted with, this is going to seg fault because I broke the T-cache. So we could do this, but so that means that I need to pass into this like R1, R2, right? We could just have the connections live outside the scope of the function. I could make these connections, pass this in. My logic from here down is good, right? And so I should be able, and this is just, programming 101. What is a function? Get read R1, R2.
Other way around, the target's first. Target address is first.
If there is a way to mistype it, I can do it, right? But we could do something like this, right? And then if I need to leak another location, we just say, all right, we're going to hang on to these. We're not gonna let them try and close. And I now have R3, R4, and I have target address 2, and I'm going to repeat this with R3 and R4. Everyone agree that I could do this? Okay. And this is a valid way of tackling these challenges. We just abstract this whole thing. We say every time I'm going to start fresh. But we run into, it's not necessarily a problem, but a kind of unnecessary thing. One, I am literally relying on the fact that this has unlimited connections, right? And that may be something that I don't really want my exploit to rely on, right? And a little unrealistic. And secondly, I have to go through the work for every time that I'm doing an arbitrary read. I have to go through not one race, but 2 races, because I have to get the race to get the heap leak for a pair of connections, and then leverage that to get the leak. And so the just runtime of this is now kind of long, yeah? Especially if I need to like pivot and read 3 or 4 ways deep. I'm now doing 8 races, each of which I have some uncontrollable chance of just losing. And this becomes workable. All right, it can get you a flag. People have done it.
I think it's gonna be painless.
Oh, none of it's painless. All right. This module is pain. But what if I told you that you could solve every single one of these challenges with only 2 connections? You'd say, yeah, of course. I know what it is. Well, what's my trick? How do I get around this problem of having a corrupted T-cache? How do I get around this? Let's think back to how the T-cache works, right? What are the 2 things I can do? I can malloc and I can free. If I malloc, I explode. Yeah?
Why would I explode?
Because this is the next address in the T-cache. If we were to look at that, is that a valid address?
Nope.
No. So if I malloc is going to give me this pointer, which, since safe linking is enabled, it more than likely will explode in a heap. And say
unaligned T-cache.
Yeah, unaligned, or it'll seg fault down there in some other implementation. If miraculously the heap implementation managed to resolve, it is possible to get malloc to return something like this. But then as soon as I use it, right, in any capacity, I'd say. Very unlikely that malloc returns it, but I'm pretty sure you can satisfy those constraints, if I remember right. So mallocing is definitely not the way to like get my way out of here. What happens if I free?
Free more stuff.
I can do that, right?
Just move the problem along.
I can push the yes. And I like you laugh, but that is actually the solution, right? I can free stuff onto here, right? And so I could push this all the way back to where it doesn't matter, right? But I could also fix it up. Like if I were to free something in here, say I free two things in. There's two things that matter. There's the count for the bin, right, for the bin size, and then there's the chain of next pointers. So if I were to free, say, two things in there, you can envision what they would look like, right? Two valid pointers that go to this insane. But I have the ability to erase and fix up the next pointers, right? So I could overwrite these next pointers and make them point to somewhere that is valid memory, to where it doesn't even follow this chain to get here. You can invent your own series of Tcache next pointers. The heap doesn't care, right? As long as they satisfy the constraints.
You could use an old.
You could use an old pointer. You could use the same pointer, if I remember right.
There would be problems if you malloc the same address twice as in the Tcache.
As long as it satisfies the constraints of the heap doesn't care, right? Within the context of the Tcache, within
the program.
Yeah, the program, like the Tcache is this optimization layer that does the minimal amount of checks that are needed to like catch the dumbest things that a user-land program could do. It doesn't do any deep cleaning thing. It's optimized for performance, not security.
And it just has mangling.
Yeah, well, the mangling is safe linking is the security feature, but as we saw in 466, it, while paying, can be reversed and worked around. Now, to get back to kind of where we were, so I have two problems that I want to avoid. I want to avoid ever mallocing this, and I want to always have some idea of the relationship between the addresses that are in this chain, right? I don't want to have a allocation from heap 1 and an allocation from heap 2 on the same Tcache. So what I naively was trying to do in a rush last week was not think and just write code. Never a good idea. What I should have done.
Like everything in one.
All right. So somebody has some idea of what I'm doing here.
Do all the mallocs in one thread.
All mallocs come from one thread. All mallocs will be from one heap. I don't care if it's in the Tcache of 2. All addresses came from from the heap of thread 1. Now, I do have to think about, and I'm not saying that I'm doing this correctly here, the order of this, the order of these allocations. One of the problems that we introduced here was they need to be on the same page. So we are making allocation or chunks of size hex 410. Yeah?
They're 400 though, the metadata.
Yeah. The chunk is 410, the allocation's hex 400. So how many will overflow into the next page? I don't know. Is Python my friend? Four. You'd think I'd be able to do that. Okay. So there's this important relationship that I need to maintain between these chunks, which is I need to know what page they're on or how many pages apart they are from each other, right? And then what determines the order of what page they're on? So like, what have I done here? This is on thread 2. These first 4 are on the same page. You agree? Assuming that we're starting at 0 for the page.
It might not be. It might be just the first 3, or maybe
the
fourth might be iffy.
Right, and so we'll have to use GDB and like look at that, right? But it would be deterministic, right? So maybe let's do it. Let's see. Give it a run. Waiting for after freeze. We are there. Boom. thread 2, bins. Oh no, bins.
Oh, we freed into thread 2, so thread 3.
Mm.
Oh, that's after. No, you're looking at the second freeze, though.
Did I put the same? I did. Okay.
Yeah.
Thread 2, bins. Thread 3, bins. And let's do this right next to each other. Oh, thread, bins. Okay. So we can use pwn debug here and reason about, are these on the same page? Hey, those happen.
Yeah, those are on the
Those are.
Yeah.
Does this guy make it? Was 4 not the right number? 3, 8. Interesting.
Oh, these 4 are on the same page.
I think after the first allocation, they're no longer on the same page.
Right. We seeded this overflows to we have, oh wait, 2B, 2.
Yeah, they go this way. They go from.
Oh, because I freed into
Yeah.
thread 2 first. Okay. So I'm at 1, 1, 1, 1. This one was 0, so this was the first one. So there is something going on, which is fine. Like, that makes sense. Somewhere before we started calling malloc, right? Something else was using that thread keeper pulling from. Cool. So I know that this one is just like, I don't want to deal with it. But I can make an assumption that these are on the same page. So now my demangle logic works. Then I make an assumption about these, that they're on the same page, because my demangle logic works. Now, how many allocations can go into Tcache? What's my max?
64.
Seven's right. I get the max. If I keep treeing, the max length for this singly linked list is going to be 7 entries.
What happens if you go to 8?
Hey, what happens if you're free in 8? You'll find out in this class. Maybe a month from now.
In like the next heap module.
Yeah. That is the distinction between the heap 1 and heap 2. What's that?
Freeing 8.
Yes. Because we can look at this pretty easily, right? And we see only thing we talk about here is Tcache bins, right? But when I type bins in pwn debug, it has these other things: flash bins, unsorted bins, small bins, large bins. All of these are their own thing beyond. Once you go to 8, we have to talk about all of these bins, and we have to talk about how they're all related. That's worth its own 2 weeks. Because that has a lot more going on than just this simple linked list.
64 is the number of bins, right? Each thread has.
I'm going to say that sounds right. I don't know.
Well, they're not all Tcache bins.
Well, no. So you're saying the number of sized bins in the Tcache. That sounds correct. I don't know it to be correct, and it is something that likely is subject to change on libc versions. Okay. So the max I can push in here is in fact 7. What I would suggest is not doing this, but say I'm going, my logic here is my code is already relying on the Tcache of thread 1. Yeah? I'm going to use the Tcache of thread 2 to just hold pointers. That's all it's going to do. Because I'm going to mess up the Tcache of thread 1 every time I get an arbitrary read. So if I load up thread 2, let's see here. Malloc, free. Let's go for broke. 1, 2, 3, 4, 5, 6, 7. 6, 7. I now have, I haven't done anything with thread 1, with thread 1's Tcache yet. I now have a series of pointers that I know the relationship to them as I pop them off. And maybe it makes sense to me to free these in the reverse order. Like, I don't care. look at it, figure out which way works right for you. What I can do from here is I'm just using R2 to hold on to good pointers, right? So then R2, I malloc something. And you could also hold good pointers in these indexes, right? I don't know, you got 16 indexes or something like that. You can hold good pointers in the indexes as well. Just hang on to good pointers. So then when we do something like this, I'll flip them around just to make it fun, right? I know the relationship between these 2 pointers. That's all I need to erase. Is that right? No, I think I need one more, right? Because I need the count. I need the count to be 3, if I remember right.
Why do you need 3?
So let's think about this.
Oh, okay, yeah.
I'm mallocing. If I have 2, I'm erasing that.
Because you want one to point to the next. And then
I want it to think that the third thing is a next pointer.
But it's going to be the value.
Yes, but it's going to be the value. That's why I had to think. Yeah, this stuff is hard. Like, this isn't stuff that I just know intuitively. Like, I mess around with it. I can reason about it, but like, in no way would I be like, yeah, man, this is just make perfect sense, right? Instead, I work from first principles, right? And I have to. It's not for your benefit. It is. I mean, it is, but it's also for mine. Because these challenges would take me time to do. And so hopefully this gets to the block at the end here. And we'll be in a broken state. And the question is how do I get to an unbroken state from here? If this goes where I think I should. That's not good. But the question is stuff broken? So I was working on thread 1 from my exploit code, which is thread 2 in GDB. We look at the bins, we let pwn debug go. It is in that broken state. How do I make this not horrific so that I can continue?
Like you said, free some stuff. We'll go on.
I go, yeah, man, you just get the flag. Wait, what do I got to do? Wait, what's my order of operations here? Right now at this moment. So I have leaked. Like, I think people are stuck on level 3.
Yeah.
Level 3, there's more than one leak that you have to pull on, right? This is my first leak. I need to do a second leak.
Malloc and then free.
Okay.
So,
from which thread to where?
This is thread 1, right? Where we have a corrupted state.
Yes. So thread 1 is I'm going to call it my exploit thread. Thread 2 is hanging on to the good pointers.
So malloc in thread 2 and then free in thread 1.
There's the good pointers, right?
Yeah.
And your statement was that I'm going to malloc in thread 2
and then free
in thread 1, and that is correct. And it's important that you do exactly that, right? And it's also important, I don't know if I got this right or not, in this case, they happen to be. Now, the nice thing here with GDB is you can always see what pointers you're going to get, which means I know right now, so the next 2 pointers I get is my demangle function, like, going to hold true, right? Is this on the same page as what I was thinking about on my thread leak? Does my exploit code say what my heap leak was? I leaked this heap.
It's a page off.
Okay, but I can subtract 1, right?
Yeah, we can deal with it.
Right, and that is what's important. That's what you have to think about when you're juggling these pointers on the T cache. Is if I can deterministically know what address, how the addresses that I get here relate to my initial heap leak, then this is just some simple addition to do the demangling instead of having to create new connections, get a new heap leak. Maybe I explode, maybe I get bad bites, etc. And so we said it was R2. We malloc. How many do I need? What I care about is the count. What is the count in thread 1's Tcache right now?
I think 3. Oh, it's 1.
It's 1. It's this one. It's this one chunk that I never want to actually get, but the Tcache thinks it's there. So if I throw 2 more in there, I've returned to kind of the state that I'm in. So I don't need to do 3 again. Let's make these actually go to different slots. And so we can do this, at which point now I know, what did I do? Malloc 1, going to give me this guy, and then this guy. And they're going to be in the reverse order because of what I'm doing. It doesn't really matter in this case because they're on the same page, which is what I care about. But you see how now I can leverage GDB, and I have to like be quite particular about these pointers in what I'm doing. I like this pointer juggling, right? I think it's kind of fun, if I'm being honest. I think it's super cool that you can do that. Does that make sense why you explode sometimes? And like why all of a sudden demangling doesn't? Yeah. All right. So I think that's kind of cool. Now, what are you guys stuck on? That's what I wanted to show.
I'm almost certain this is what solves my problem.
Good. It's a good thing when I demonstrate something that's useful. The standard one for Twitch is I'm pretty sure this solves my problem. And that's the sign of a good demo. Is anyone stuck on anything else? If not, I can talk about some other pain points that you can run into. Do you know why you're exploding or what you're stuck on? Have you tried it? If you haven't tried it, then I have no mercy, right? It's just like, okay.
I asked earlier in the class if we could go through GDB and see if we can like break at malloc and see what's actually being malloc, right? Just to see like make sure our for like a scenario, just checking the demangling happens as we expect it to happen, right? So we could. What my thinking is, could we go through GDB, break right before malloc, see what's about to be malloc, so the mangled address, and then finish out malloc, and then see what got demangled from there. Just as in my scenario, just a sanity check, just to see through GDB.
No. I'm just trying to understand what it is that what we're showing, so I break at the right spot. You want me to break before a map call to malloc, and then look at the Tcache and look at the value that's returned?
Break at malloc, so right before a malloc will happen, check the address that's going to be grabbed from the Tcache, which, now that I think of it, might not be mangled, or it would be mangled.
So maybe and like the mangling, not mangling, becomes a bit tricky, especially when we start talking about things like pwn debug. Like we start using GDB and GDB plugins, because there's a difference between, and I don't know the answer here. Like I would have to, we'll discover it together. So I am somewhere. Where am I? Okay, we'll go all the way. The GDB plugins will try and be helpful. And so I don't know when I type like bins, is it showing me, actually, I'm pretty sure pwn debug is doing the demangling for me in that bins output. But we could examine giant hex at the address that the bins is showing me to see the mangled next pointer if we look at the literal memory.
Right.
Okay, so we're at this, is stuff broken? We will go to, I guess I'd have to go to thread 3. because this is the one that does have some stuff in the T cache.
We'll examine giant hex.
Right. We'll examine the giant hex that is here. That is not this value. Do you agree? And so pwn debug is showing me the demangled value here.
But when we are able, yeah, this is how you would see before I allocate what the next pointer would be. That's something like this, similar to this.
So this is telling me right here, right? This is the head of the T cache, right? The head of the T cache is this value. So the next malloc is going to return me this point.
So there's no way to see that mangled.
If I wanted to see this mangled, I would need.
Wouldn't you VM map and then see where the is the T cache been in VM?
So when it is in the, you wouldn't even, so the head pointer itself, if I'm remembering right, we'd have to look at glibc source, but from memory, this address would be in the tcache per thread struct as the head pointer. It is demangled when it goes into the head.
Oh,
right. And so if I wanted to see this mangled, what I would need to do is I need to free something else onto here to push it back, and then I could examine the one before it. So like I want to see this mangled, I look at the next pointer of this right here. I don't know that that's the absolute best way of doing it, but it is a way that will work. Does that get you where you need?
Yeah.
Okay. So there's definitely a lot of thinking about the mangling. Is this right? What are the addresses? How do I deal with it? Right. Twitch. Do you remember? Because I do not. I'll Google it if I have to. Twitch, do you remember what the equivalent of Jeff scan is for pwn debug?
Find.
Well, no. So there's find, which is a built-in GDB command. If you have the Jeff plugin, there is scan, which is I'm a Jeff person, so I like scan, except for when Jeff horrifically doesn't work, like right now. There is an undocumented command in pwn debug that does the same thing as Jeff scan. I think it is P2P. Thank you, Hanta. So when we VM map, we get this output. The thing that you want to do when you're pivoting around memory is for like level 3 is I get a libc leak, right? And I can find that. Let's look at bins. I want to find this region of memory, which is going to be one of the thread heaps, right? Cool. I want to scan this region of memory. Let's see if this works just like Jeff. We're going to find out for libc. This is showing me, now you have to think a little bit about how this is working. It's actually just kind of grepping. So I'm grepping for this, which is hopefully a unique string. I'm saying, show me pointers from this region of memory. You can also, at least in Jeff, specify literal address ranges. Show me pointers in the first address range that point to the second address range. And so what we see here is these are addresses in the thread heap that point to a libc address, hopefully. Oh, so this is telescoping. Okay, these are, those are libc? Is that libc?
Yes.
Okay. So there's another thing that you can do called telescoping, which is where you basically just dereference a pointer. And if that's a pointer, it dereferences another pointer, which is what it's kind of showing here. By dereference. And that can be a trap. But yeah, we VM map there and we see that is a libc address, right? Jeff's equivalent command is scan. Super handy, right? Because if I get a heap leak, which I have, like this right here, just like when we think about the stack, there's nothing stopping me from taking my leak and say, how far away is that from, it's going to be the other way around. You take the big number minus the small number. Where did that end in? 8? Is it 80? Yeah. Okay. Nope. I don't know what numbers are big, man.
Parent/x for x.
You think? BD 793 BD4. Yeah, I took the small one minus the big one. I want to do that. There we go. And then we'll.
That seems a lot.
That does seem like a lot.
You might have messed with the first address. The heap address might be wrong.
You think that's wrong?
Yeah, there's an extra B. There's a 2-3.
Oh, okay. All right. All right. Thank you. Math isn't mathing. All right, that's a reasonable number. And so just like when we were in 466 thinking about contiguous memory on the stack, all we needed was here is some pointer into a contiguous region of memory. Here is some constant distance from something I know to something that I want. I can perform addition and or subtraction to figure out the location that I want to leak. Right? See how that neurons firing, things connecting. So level 3, where does it want you to go? We're all stuck on level 3.
There is a stack.
Read from the thread stack. Okay. So yeah.
I think that 80,000 thing is the heap stack. Yeah.
So let's say I want to go there. And I have, what was it? libc, p2p, libc to this thing. Now, since I don't know if it's like interpreting square brackets or not, but assuming that it's like a same normal grep thing here. When I say libc, it is going to look at any region of memory that has libc in the help text over here. Now, an important thing to be aware of, whether you're using P2P or you're using JEP, is I am being lazy by just saying libc, right? I'm saying I'm only interested in these regions of memory. Nothing. All right, that's a bummer. Totally fine though. Is there anything contiguous to these regions of memory? Well, this ends in df. This is df. Does this have libc in its name? No. So I didn't search for this region right here, but it is something that is contiguous with my libc link. And so it may make sense. And for, I don't know if it's this level in particular, but I know in some of the levels, it makes sense to, instead of just doing this kind of lazy libc, specify the full range of contiguous memory. Because there may be a pointer that is contiguous with libc, but it is not libc. A good example of this, if I remember right, is you can go all the way down. If we follow this, libc, df, 3df, 3df, 3ee, 3ee, 3f0, 3f0, that all looks contiguous, right? In fact, if I have a libc leak, I can go all the way down here to the loader. All right? And so, woo, not that. I don't know if this will be successful or not. But yeah, I did not know that would work. But it was a good example of, well, we need to think about the literal contiguous memory. It's a far ways away, but can I get an address from libc? If this is all mapped contiguously, that's just a bigger delta. I found a pointer to the next thing I'm interested in. This whole assignment, this whole module reduces to the two things that we've done. All right?
So, do we have right now enough knowledge to progress through the rest of the levels? Or is there like a concept we still have to tackle? Okay.
This is literally it, right? This module used to be, like way back several years, part of system exploitation, right? And then as we shifted content around, it didn't make sense because we pulled heap 1 out. at which point I can't throw this in there because you don't have an understanding of the heap. Right? I think it makes sense here as a continuation of system exploitation because it does do a lot of knowledge check. We have to know heap, we have to know race conditions, we have to have some idea of all of these components, reason about memory, GDB, etc. Right? And then it also is kind of a programming ability check, right? I showed you I could just tab all this thing over and say arb read, but you can, and you should, in my opinion, wrap these things up so you do have right functions like get leak. It's going to take R1, R2, and it's going to take a target address, right? Now, maybe this thing requires you to have your race where you're doing this alternating. You may have to do an arbitrary write. What's going to be different about an arbitrary write?
Instead of a scan.
Yeah, instead of a printf, we do a scanf. I hope that's not a deal breaker to you there.
I might have to drop.
And we can say that, right? And kind of joke about it, but it's still hard to generate this stuff, right? So I don't know. Let's see. Is hex 90 a horrific byte? There are horrific bytes. Let's see. Is 90 one of them? I feel like no. 90 is Z. No, it's not. What is 90? Hex. Oh, it's too far away. It's not ASCII. So there are bytes that are just garbage, right? And as part of this assignment, you need to pass bytes into scanf, and you need to get bytes from printf. Both of those will print out or produce output or take in input conditionally based upon the bytes that are provided or output, right? What I pass into scanf. If scanf has a space in it, what is space? All right, somebody knows that. It's hex 20. If I try and write something, an address that has hex 20 in it, I cannot get that through scanf. You will fail.
Is it possible that you get unlucky?
Yes.
Address where the secret has a space?
So the question is it possible that I get unlucky? And you specifically are asking about the address of the secret, which for like level 1 is into BSS, which is in a fixed address. In that case, we do test against it because this is consistent. Like every boundary that you have is solvable, right? Now, it is possible, like when we say, Twitch asks, it's just white space that doesn't do nice with scanf. That is my understanding, yes. And we could know that by looking at our good friend, the man page. When we look at what the challenge does for scanf, it is using printf. Oh, okay. It is going to take in 1024S. And so what I'm interested in is what happens with the format string of S. You find it over here, and it says, good, it is following me. It matches a sequence of non-white space characters. The next pointer must be a pointer to the initial element. And it will also deal with null. I don't know if you consider null white space or not. But yeah, white space characters and null will ruin you for trying to write something in. Now, it's interesting to note, well, if null ruins you, and we look at some of these pointers, where was I? In bins. There's a null byte there. How does that work? Well, were we writing these literal addresses? No, we're writing the mangled version of these addresses. And so it's not the null byte. I can pass in a mangled version of these addresses. But the problem that you run into that is part of just the randomization of these addresses via ASLR is what happens if the mangled address has a null byte, or the mangled address has hex 20. Can I write that? No. Now, there's two ways you can deal with that.
Mangle different things.
So one statement is you could mangle a different address. Maybe. So it depends on where we're going to use hex 20 as an example. If my address ends in hex 20, will I ever win that with ASLR?
If the address mangled that I'm trying to write has
let's printf goes for a null byte, so that's fine. Yeah. So I'm trying to write in a mangled address that ends in hex 20. I will never be able to do that, right? And the reason I'll never be able to do that is the least significant byte is not randomized by ASLR, right? And so that will consistently fail, in which case I would need to pick a different address.
But do we need that exact address, or can we get somewhere in the neighborhood of the address?
Depends on what you're doing, right? Like that's the question was, do I need that literal address, or can I fudge it a little bit and pick something nearby? The answer is that depends on what you're trying to do. Like you couldn't just increment it by 1, for example, because you would fail the Tcache alignment check, right? You need the least significant nibble to be 0.
Or
so
8. I'm pretty sure it's 0 or 8 to get out of line. 16 byte.
I'm pretty sure it's 16 byte aligned with safe linking. So without safe linking, it is 8 byte aligned. With safe linking, it's 16. It's 16 aligned. Is from memory. But yeah. So if the value that I'm trying to write, the least significant byte, has a forbidden value, pick something else. What happens if this is, I don't know, where's some pointer? I'm trying to leak this address here just arbitrarily, right? And it's 7FFC720E20000.
Restart the challenge.
Restart the challenge. Yeah, no, you're 100% correct. Because that hex 20 that I am trying to write in is impacted by ASLR, and you just got unlucky, right? Now, you could just, have a little bash for loop, right? Keep running my exploit, but you're going to blow up in all sorts of strange ways. And if you try and attach a GDB to every way you blow up, and half of them are due to ASLR, this is a huge time sink. This is where just writing better code is the solution. So if I have some function that is essentially what I did up above, and it is read, R1, R2, target, I'm going to have some mangled target that I'm going to try and write, which is going to be a mangle of my target. I should check this. And I should my recommendation is to use an assertion. Everyone know what an assertion is? An assertion is a line that you add in your program where it's just, this is a fact that must be true. If it is not true, your program will explode early. You'll get an assertion failed, you'll get an error message that says why you failed, and it will just exit. And so I can assert, for instance, if this is a number, let's say mangled bytes is going to be P64 of the mangled target, because I'm assuming this is a number, so now I have some bytes. I can assert that the byte hex 20 is not in mangled bytes. Okay? And there's more than just hex 20 that you're going to run into. I would start keeping a list of bytes that are going to be problematic, writing these assertions and failing in your code early. Because then you don't waste time debugging whatever insane thing happened when you weren't able to properly pass input or you weren't able to properly get a leak simply due to ASLR. Common problem. And it will happen if you just run a bunch of times. There's nothing stopping this mangled heap leak from having a forbidden byte and this exploit just exploding. I just got lucky on this particular run. And the more arbitrary reads you're trying to do, the more opportunities to fail you have. So you might want to try and add early exit logic here to make your life easier. But that is this entire module. This entire first half of the course is about, I wanted to make slides and didn't get time. This entire first half of the course is about this concept of primitives. Because when we talk about more complicated exploitation, everything breaks down to, you have some weird machine, right? Maybe it's the T cache. I need to generate a primitive that allows me to read a memory address. Maybe it's, as we'll see next week, printf and format strings. I'm going to abuse that machine, and I'm going to end up with a function that does the same thing here. It's an arbitrary read. I pass it some address. It lets me read something. And we can start thinking about exploitation in terms of, I get an arbitrary read, therefore I can do X. I get an arbitrary write, therefore I can do Y. And then we can start talking about these things abstractly instead of, oh, here is a heap thing. And you can start talking about, well, I got this primitive, and as soon as you get, for instance, an arbitrary write, assuming there are no constraints on where you can write, there are known paths to take an arbitrary write to, for instance, getting control flow. Then you have execution, you can do whatever you want, right? And we can start looking at how we can leverage these primitives to move forward. So then the game becomes, here's some weird system, how do I get a primitive? Here's a weird system, how do I get a primitive? And that's what we'll see over the first half of this course. All right, there's supposed to be a break. I don't know how long I've talked, but it's felt like forever. So I am going to make this guy pause for a bit. All right, I think we're back. In case you are a student that is not here in person, I did ask the class what their preference was for office hours. Tentatively, I said last week we do them on Fridays. People seem to be indifferent on whether they're in person or not. So I think I'm going to do them on Discord. And if you do want to like sync with me in person, let me know. I won't have a room reserved, but we can meet up here on campus, like up on the fourth floor in a common space and deal with whatever we got there. Then just let me know. And on that note, I had some people message me on Discord and ask where can I get help. Hopefully, at this point, you have gone on pwn.college. You have found our dojo, which, to be fair, was not accessible the day of class. I fixed it right after. You can go to CSE598 Spring 2025. You do not get this admin button, but you should be able to click on course. And then from here, there is identity. And right here, it's important that you put in your ASU student ID, MASH update, and then verify. Unlike me, you have 5 green check marks here, and it says set up, good to go. That should communicate with our bot, grant you the ASU CSE 598 Discord role, which gives you access to a couple course-specific channels. There are public-facing channels, but given the class size here, I don't have a problem doing most of the discussion in the class channels, if that's what you guys like. I know there are a number of options. Just let me know what you prefer. Ping me from wherever you post a question, and I'll try and work with you there as well if you need asynchronous help. All right, so one of the questions that somebody asked was, all right, is this enough? And they asked earlier, is this enough for me to like burn through this module? And the answer was, I thought so. And then I was clicking through these, and as we look through, these follow a very similar pattern, where for the description, we're going to use an arbitrary read, and we're going to read it from somewhere else, right? One was the BSS, 3 was, we said, the thread stack. And as we move through this doesn't tell you apparently where it is. I'm sure you can find it. Now we're going to leverage read and write primitives. Sure, why not? But when you get to 9, this is something a little bit strange. I had a chuckle because I forgot I did this. It says create and use arbitrary read and write primitives with less control of the heap. And that's kind of ambiguous, right? Like, what does less control of the heap mean? Good question. All right, looks normal. Looks normal. I did pick a 0.0, right? Yeah. So one of the things that I'll say in more advanced heap scenarios you need to deal with is, what if you are not the only person on the heap? All right. Now this can manifest in a variety of ways, and this is a somewhat contrived scenario, right? Because this is a 0.0. I tell you the size that I'm doing it, and I'm only doing it when I malloc something. But we see every time I malloc, before I do, you get yours, I get mine. And so this is going to influence.
Oh, I see. Okay.
Every time
you do a malloc 0 with that size, and then it does our malloc.
Yes.
I see.
So you malloc for, like in level 1, it was hex 400, right? Every time you call a malloc, it's going to malloc to nowhere of an arbitrary size, and then give you a malloc.
What size?
Well, we've done this a few times now.
I think our malloc is still the same size.
Oh yeah. So let's tell me how we figured this out. Yeah.
IDA.
Okay. IDA works. These two challenges are not challenges that people. I really enjoy them. Right. I really enjoy them for a couple of reasons that, depending upon where you drive this, we'll get to see the difference between 9 and 10. So this is going to follow a very similar logic to what we saw before, so we're not going to waste any time there. We'll get to run thread, we'll get to challenge. The kind of obvious place right now that we've seen where there is a difference is when we malloc. So when you type in malloc, it's going to get the index. It's then going to choose a random size that is up to hex 4000. It's then going to do that allocation. And then it will perform your malloc, which in this case, it looks like it's still hex 400. There's really no impact to you what bin I pick here. The name of the game is still the same. So I don't think this is a critical number. But what we're doing up here is, because we spent kind of the first part of the time talking about the importance of knowing what page you're on for this mangling and demangling.
But if it's mallocing random sizes, and this is me just thinking.
Yeah, we're spitballing. We're looking at this and being like, what have you done?
Right? Yeah, I'm seeing what's the handicap here. Like I'm just trying to understand.
Okay. You could be put in different bins, right?
Right. I'm thinking if we're all mallocing for 400 and freeing 400, isn't our Tcache not affected by this random size?
In theory, this still works, right? I can do .pi. We can.
I think the issue comes when we want to malloc something from our Tcache, but then the random malloc.
Yeah, but it's making a random size, so it's not necessarily taken from the Tcache of 400.
I agree. It may or may not touch your Tcache. What does it impact?
That's what I'm trying to think through. I don't know.
So this will probably explode. Nice. It did not explode. So I ran the same exploit that we had, right? And the thing that I'm really interested in is the Tcache, because you're like, hey, what is this even doing? This is going to do nothing to me. Oh yeah. Oh, that is interesting. What thread did I go on? Info thread.
We're on thread 2, actually. So thread 3.
Isn't that where we were? Oh, I ran. Oh, no. So that is right. Okay. So I ran the same code, and I ran do.py. I was mallocing and freeing 7 things from 1, and then I freed them into 2. And then I look here.
But this is after our whole thing ran.
So where do you want me to look?
Could you check GDB after freeing 7? So R2 7937. So waiting after freeze.
We'll call this one 1. We'll call this one 2. Which one?
The first one.
First one. Okay. See if I can type. Thread 3 bins. What has changed?
We have bins of 300, 250.
Okay, so we have these other Okay, whatever. Right? But what has changed about what we care about, which is the bin for 410. What is different about these pointers?
Oh,
It's made no difference at all to what you have to do, has it?
They're no longer on the same page.
Oh my gosh, they're no longer on the same page. And that was something that was like this huge problem when we started this class, right? It was really easy and we could get around it because we just malloc everything contiguously from one thread. The act of mallocing before you malloc is going to change what your initial mallocs are getting. Because when the T-cache is empty and we're calling malloc, you can think of it as the heap is just, this is not the heap. So some region, this is the stack, but it is some contiguous region of memory, right? And there's like, this is, as Jan calls it, the wilderness, right? This is the edge of stuff that's been given. Beginning, we have given you nothing, so the wilderness is the beginning of the heap. We give you a chunk, the wilderness is now here. You ask for something else, the wilderness is now here, and we just extend the wilderness out. When you're the only one doing the allocations, every allocation you get is right next to each other. This is very easy to reason about. If there are other allocations happening in between yours, you can no longer make that assumption. At which point, now my math has gotten kind of hard.
But you still have two chunks, right, on the same page.
It just happens to be this time.
Do I?
The
The
one after 650.
Okay, so these two happen to be.
Yeah, it's coincidence. So
It's coincidence?
No.
well, it depends
These
on
two are
how
on the
we
same
malloc.
page too.
Depends on the malloc before us.
Right. So the statement is it depends on the malloc before us and what's the spacing between them. Right. You understand what it depends on, but you're saying it's coincidence.
But they come.
But this is like they may not. Like you see the code that's happening, right? I'm randomly doing this. Now, I'm going to save you a little bit of headache because you made this statement that this is coincidence, and you made an observation about these two pointers, and you made an observation about these two pointers. Yeah.
And there's two more actually.
Well,
That's the same one.
Okay, so you want these pairs of two. That's cool. Which one were we on?
The first, yeah,
This one? Okay. Does this hold true?
it's hold.
Okay. Now that's strange. I said that I'm doing this randomly, right? Is this coincidence? Am I just lucky? How can we reason about this? My first number is 2F2. I'm going to restart the challenge. My first number is 2F2.
Why is it 2F2?
I don't know. Why is it 2F2? So how does RAND work?
You take a seed and then
Yeah.
generate a
This is not coming from /dev random, right? I'm calling RAM. And as somebody pointed out here, the way the RAND function works is you need to seed it. You need to seed it with the value, right? And so in level 9 here, if you were to dig a little bit deeper here, you'll see that this is consistently seeded. All right. So that means that, okay, we could parse some of this. We could do some math. You could do all that math. And you can succeed doing it, right? You can write an exploit that figures out what is the chain of random values that occurs in level 9.
That's the difference.
Well, what do you think is going to happen in level 10?
Dev view random.
I don't think it pulls from dev view random, but let's just test our theory here, right? 2F2, great number. Why am I over here? Where? All right, with malloc 1. Okay, so there's several of them. Is this consistently seeded?
What is it? Your flag is
flag.
yeah, the democrat.
I don't know. Why is it saying that? That's a little
privileges.
little bit weird. Huh? So one of the things that you can do, as I kind of said, when you have arbitrary read or arbitrary write, yeah, is you can leverage that to get control flow execution, right? We in 466 we messed around with the PLT and GOT, right? So if, for instance, there was no railroad and you had an arbitrary write, could you overwrite like a God entry to call like a win function? Yeah, you could. Could you overwrite a return address and return to somewhere that's interesting, right? Could you ROP?
Yeah.
Yeah, I mean, if you really wanted to leverage arbitrary writes, you could overwrite the stack and write a ROP chain to the stack to get it to return to then ROP, right? I mean, these are things you already know, right? It sounds like pain to do that, but these are things that one can do. If I drop privileges, does this stop you from doing any of those things? Yes, because you can gain control flow, but you can't cat the flag, right? Now, you may not be doing that right now, right? Leveraging an arbitrary write to gain control flow, to pop a shell, to cat the flag. But there are clever people who have,
Oh.
right? It was, I think, the first iteration of this course that I taught. There are some very talented individuals. And when in doubt, they would return everything into ROP. And it drove me mad. You can still do that for a lot of challenges. Because if every challenge reverts to, I get an arbitrary write, I turn this into ROP, I then call system, right? I call set like a one gadget and just pop a shell. Well, that's really lame to me. So much like when we have kernel challenges, or that kernel challenge where we like delete the flag, we'll go out of our way to do things to prevent stuff that you may not even know you can do because somebody's done it. Right? And so this tells us, if we reason that this is actually reading the flag, let's take a look. If that's a troll or not, I don't know. Could be a troll. You can't, you can't really trust the challenge help text. Bam, 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 bam. Run thread, which is a wrapper around challenge. Challenge. Okay. Okay, this one might be a troll. This one might be a troll. So this one does read the flag, right? And so the question, this one might be unfair. This one might be unfair to you guys. The challenge does read the flag. I'm going to tell you, which is unfortunate. I should have thought about that. This fread call, this is a good thing we looked at it. This fread call utilizes a file struct, which is something we talk about 2 weeks from now. I'm going to say that this does result in the flag value being written to a region of memory that you can already access. So, like, when we think about libraries, like the reason that when you close a connection, sometimes you will explode, like you'll segfault, is because there's nothing stopping a library from leveraging the heap to do whatever it does, right? a library can malloc, utilize memory, free it, and it should assume that the heap is reasonable. This is going to leverage the heap. The act of calling fread is going to, as part of the implementation of a file struct, create an allocation on a heap where the flag goes.
And this is covered in file structs.
Yeah. That's fair. That's fair. That's on me. See, that's really good call. Otherwise, this would have, like, I would not have expected, without me saying that, you guys to necessarily figure that out. But it is reading the flag, and the flag will end up on the heap as part of calling fread. Because fread is part of standard IO, which has a more complicated way of the buffered reading, where everything we've done so far is like read and write. When we call fread or fwrite, this is a buffered reading, which means as an implementation detail of the library, it may leverage memory to make the call of getting bytes to and from something faster. And part of the implementation of how it does that is by leveraging the heap. The reason that you would explode when a connection closes is because there may be a cleanup routine, right? Like you have standard in and standard out, right? We just kind of, oh, it's 0 and 1. Well, that's kind of true. It's true in the literal sense of file descriptors, but standard in and standard out are actually these more complicated file struct things. And so there is a flushing mechanism. That's why sometimes you may notice that bytes don't flow in or don't flow out, and it's the magic of buffering. And the magic of buffering exists in this file struct nonsense. So I had to give that away. That's fair. But what we will also see somewhere in here call rand. What do I want to seed? I need srand. Somewhere in here, we call srand. There's this level, srand, recall. Bam. So this is where it's seeded. And this is seeded. So srand is how you seed the random number generator. And see, where is it seeded from?
Seeded with the blood.
Well, that would imply that it's consistent. I am pretty dang sure this is not. Because if it were seeded on a consistent value, these two would be the same, and they're not. The intention is level 9 is determinist, and so you can put in that work and do the math if you want. Level 10 is randomly seeded. It's seeded. It is true random. So I'd have to look and see where it's. Maybe it's sranding again or something. But we see that this is not deterministic, and level 10.1, for instance, is not going to even have this help text as you would expect. So there is a way to get a heap leak that is deterministic. There's a deterministic solution to this where you can get a heap leak and not have to do this math. You don't have to do the math on 9, and you don't have to do the math on 10. You can't do the math on 10 because it's actually true random. These last two, we'll see how it goes. But the first 8, I think, are fair game.
I'm aiming for the first 8.
So I think the first 8's fair game, right? If this has terrified you a bit, that's okay. All right. The next module is
manage expectations.
Much more approachable. All right.
Format strings.
Yeah. So I personally really enjoy format strings. The reason they exist is because I really wanted to bring it back. They were taught the very first year of home college, and then they removed it. And I was like, no, because people claim there's a very vocal group on the internet that claim format strings are just irrelevant. Like it's a solved problem. They aren't real bugs. We shouldn't teach it. But every couple years, somebody messes up a format string on something critical, and that proves to not be true. So I think it is worth teaching, even if it isn't something that you see that often. Historically, which is why level 10 has this thing that is totally unfair with that F read. Historically, this module was a midterm for 598.
This is our first module.
Well, if you go historical before that, this was in 466. Right. So it just depends on, what year you want to look to. But yeah, it's a strong start. If this is super spooky, it's okay. Right. We will roll with it as a course. I am not trying to destroy you, but I do want to give you fun challenges that have interesting elements to it. Right. That challenge you to think about it. Like most people that have solved 10, like they didn't just sit down and do it on their own, right? Like the Discord discussion is helpful, right? Please use it because these are challenging in ways that, and it's true for a lot of this course, where those, particularly the last couple challenges, go out of their way to do something troll-ish, right? Talk about it. I'm not gonna destroy you for talking on the Discord, right? With that, I don't have anything else for the stream, unless you guys do. It is roughly 2 hours in, which was my target there for the stream. So I'll give it a moment for the Twitch delay. We'll end the stream, and then if you guys are stuck on something in particular, we can sit down, take a look at it, or throw it up on here. We just won't share it with the greater internet. All right. Good. Twitch. You seem happy? We'll call it there. Goodbye, good luck. Format strings will go live on Friday. And